Death of a high mass star. So again, we are starting where we left off, where all stars end as a red giant, where you've got helium fusion in the core and a hydrogen fusion shell. Now we saw with the low mass stars that that's the end of the process. Once the helium fusion stops, the star dies. With a high mass star, it's going to be hotter. And so that's going to allow it to do more in its death throes than a low mass star. So with our high mass star, we're saying that that's a mass range of 12 to over 40 times the mass of our sun. So remember, SM is solar masses. So in terms of spectral type, we're looking at O and B stars, definitely, and the upper end of the A stars, the higher mass of the stars that fall into the A category. So as we saw, it is hotter. So that means we can get even more and more fusion, because of course a heavier element has more protons, which means there's more repulsion, which means it needs to be hotter and moving faster in order to fuse. So our low mass stars couldn't get the elements moving fast enough for fusion past helium. So it's only our high mass stars that get hot enough to create the extreme conditions necessary to fuse heavier and heavier elements, because every time a fusion process takes place, you're creating something with more protons, so it's heavier, it has more repulsion, it's going to resist fusion more and more. Ultimately, what we end up with is a core of iron, and that's what we see here. Fe is the symbol for iron. And surrounding that are all the stages of fusion it has gone through. So we've got hydrogen fusion, helium fusion, carbon fusion. So this is where it deviates from the low mass stars. So after the red giant stage, we'll have a stage of carbon fusion. That produces neon, and you'll get neon fusion. More oxygen, so you'll get some oxygen fusion. This is silicon, not to be confused with silicone. Silicon is like what's used to make computer chips. So you get silicon fusion, and the product of silicon fusion is iron. And iron will not fuse. It will fuse if you put in more energy than you get out. So nature will not do that naturally. So once you get to the point of iron in the core, surrounded by all these shells of fusion, and then of course, the star itself is extending out way, way beyond this. So we've got this supergiant star. That is humongous, very, very bright, very big. Once you get to iron, we're stuck. So, since there's no fusion in the core, it's going to contract again. So you've got this iron core collapsing inward. You've got all these layers of fusion going on outside of the core, and then you've got this giant outer shell to the star. Well, that iron core collapsing is going to suddenly stop. And it is a very abrupt stop. So picture, like dropping something from a tall building. So here you are dropping a book. That book is falling, and then suddenly it hits the ground. It stops suddenly. Well, the same sort of thing is going to happen to that iron core. What makes it stop, we'll get into that when we talk about the stellar corpses. But for now, we'll just take it for granted that that is going to be a very, very quick, abrupt stop. We've talked about events taking millions of years, hundreds of millions of years, and saying that's a short time. Here we're talking about events that are going to take place in a matter of seconds. So insanely short times. When it stops, it's going to kind of rebound outward. And when it rebounds outward, all of that stuff, all those layers around it, are going to have been falling inward, and now they're getting pushed back outward. So everything's going to get pushed out, and it's going to be an insanely violent event. What we see is what we call a supernova. It will be look like a very bright star. Historically, supernovas have been bright enough that you can even see during the daytime. You can read by it by night because it's so bright. We have not had a supernova in our galaxy since before the invention of the telescope. It was the early 1600s, I think, was the last nearby supernova. We've seen them in other galaxies, but not in our own galaxy, not in the Milky Way. We've seen them in little galaxies that orbit us and other galaxies far away, but one that was actually in our own galaxy, visible to the naked eye, not since before the invention of the telescope, which seems terribly unfair. So this thing, insanely bright, it'll be bright for a few months, a few weeks to a few months. Depending upon the supernova. And then it will slowly fade. Now that explosion of shooting all this stuff out is going to be mixing all those layers. And so you've got hydrogen, helium, carbon, oxygen, neon, silicon, all of these things slamming into each other. So you're going to get all these different combinations of fusion taking place. And when you do that, you're going to produce every other element in the periodic table. So, everything all the way up to plutonium and Einsteinium and all those things at the high end of the periodic table, down to lithium, which is just heavier than helium. So, anything that is rare in our universe, or rare here on Earth, came from a supernova. If you have jewelry made out of gold or silver, you are wearing supernova remnants. You are wearing material that was forged inside of a supernova. And the rare elements in our blood, the rare elements in the foods we eat, everything around us came out of a supernova. So again, this connection between us and the life cycle of stars is very much true. We are very much the children of stars. And Earth would not exist if a high mass star had not died before us to produce the things that our planet and we are made of. So we can thank our existence to the death of a high mass star.